So now that we formed our gate oxide and grown it, we need to put the actual gate on top of the gate oxide. Now, in general, for silicon, for the last several decades, older processes would actually form the gate material with silicon. Because as it turns out, trying to grow additional silicon on top of silicon oxide or silicon dioxide is it's an easier thing to do than forming, like, even though we call transistors MOS, metal oxide semiconductor, turns out that it's easier to continue working with silicon. So what we wind up doing next is we'll deposit a layer of silicon on the silicon dioxide gate oxide. The thing to keep in mind with trying to deposit silicon on silicon dioxide is it does not form a single crystal, because the silicon dioxide is not a crystalline structure, and so as silicon is growing on top of silicon dioxide, it can't follow the crystal structure and keep a single crystal structure. So what winds up happening is when we're depositing silicon on silicon dioxide, multiple silicon crystalline seeds will start at the same time in multiple places. Each seed of silicon will start forming a crystal in a certain orientation on top of the silicon dioxide, but each seed is going to be a slightly different orientation than another seed. So this winds up growing something called polycrystalline silicon. It's also then, instead of calling it by the full polycrystalline silicon, it will also be called polysilicon or just poly. So as we grow silicon on silicon dioxide, we'll get what's called polysilicon. Now, poly by itself, just as grown, since it's just silicon, it will have a high resistivity similar to just pure silicon. So unless we dope it with impurities or combine it with some other material like a refractory metal, it's going to be pretty high resistivity. So typically we'll wind up doping it with impurities in order to get a lower resistance poly layer. Just an additional comment about gate formation. Modern process technology will use what's called a self-aligned polygate, and I'll get into that in the next foil. And then in the newest process technologies over the last maybe 5 years or so, they've actually gone back to using a metal gate instead of a polygate, and so it turns out that we're actually gone back to metal oxide semiconductor in the latest process technologies. But the self-aligned process steps are the same for the metal gate as I'll be going through in the next foil, talking about how it works for the polygate. So the next few foils, I'll go through the actual transistor formation in modern processes. It starts with self-aligned polygate and then completes by forming the source-drain regions of the transistors. So, self-aligned polygate, basically what this means is the polygate becomes self-aligned with the source drain regions of the transistor. In older processes, the gate used to be formed using kind of separate masks and patterning steps than the source drain regions, and so you could actually have the gate slightly offset relative to the source drain region, which would cause a lot of additional parasitic capacitance between the gate and the source, or the gate and the drain. So I'll go through how the self-aligned polygate process works. In the figure below, you can see the steps, and we'll start going through them. So the first thing we do is we form the gate oxide over the entire substrate wherever the transistors are required. After we form the gate oxide, we'll form polysilicon everywhere on top of that oxide. Then we're going to pattern and etch the polysilicon away wherever we don't want it, and only leave the polysilicon where it's desired for having our gates, or potentially for having some interconnect, so connecting your poly between your NMOS and PMOS transistors, where it might run over the field oxide areas between transistors. Typically we don't use poly for extensive interconnect, but to connect between PMOS and NMOS transistors that are all very local to each other is where you would leave it. So that covers step C in the figure below. After we have the poly patterned, then in step D, we'll etch away the gate oxide only in the regions where we want the source drain regions. So this requires an additional patterning step to expose where the source drain regions are, and then we'll etch away the oxide just in those regions. Lastly, after we have the source drain regions exposed, we'll implant our source drain regions for PMOS or NMOS devices. Each will have to be done with a different masking step and implant step due to different doping materials. So, for example, first you'll pattern and expose your P-well regions, which will have N+ implants in them to create your NMOS devices, and then do a separate patterning step to expose the source drain regions in your N-well areas, which will have the P+ implants in them. And typically this first implant that's being done is a fairly shallow, so shown here is the P-well regions. It will be a fairly shallow N-doped source drain region. And the reason why you want shallow and lightly doped drains is because if you have really high concentration of doping, you get what's called some hot electron damage, where as there's current flowing through from the drain to the source, that current can effectively start tunneling through the oxide, and it's more likely that that happens, that type of tunneling effect, if you have really high concentration of dopants where the gate oxide is. And so doing a shallow lightly doped drain, it will improve the immunity to hot electron damage. It also helps suppress what are called short channel effects, which I won't go into in this processing talk, but in other talks I will. So these are the steps to produce the initial self-aligned gate with the source and drain regions for your transistors. So now that we have the initial definition of our gate, source, and drain, we have to finalize the transistor by effectively making our source drain regions better than, if you remember from the last slide, I said we had this lightly doped source drain region. That has good effects for hot electron and short channel effects, but the lightly doped source drain regions have a much higher resistivity to them because of the light doping, and that is actually not a good property for a transistor. So the steps that I'm going to show here are a way that in modern processes you get a better resistivity to your source drain while keeping the benefits of the light doping for hot electron and short channel effects. So the first thing that's done in the figure below, you can see in the step A, is we form a silicon nitride spacer along the vertical sidewall edge of our polysilicon. And so we basically now have our polysilicon gate has this additional width to it that is this silicon nitride spacer that was grown along the edge. After we define and grow that silicon nitride, we implant a new deeper and higher doping source drain regions. So you can see in the figure we now have the N plus source drain is deeper, but only in the area that's spaced out a little bit from the gate. So right near the gate is still a lower doping, not as shallow, so more shallow source drain region, and then a little bit spaced out from the gate is a deeper, much higher N plus doping region. So this reduces the resistance of our source and drain while keeping the lower doping right next to the gate. That helps with our resistivity and reduces our resistance. So after we've done that implant layer, and then in step B you can see what's done is they add a surface layer of silicide, basically a refractory metal, to the top of the source, the drain, and the gate. So that's added. They basically react with the existing silicon there in order to produce the silicide, and this further reduces the resistance of all three of those layers, thus improving your performance of all of those layers. So lower resistance in general is always better, and so that silicide layer will give us lower resistance in our gate and source and drain. Finally, we wind up growing a thick oxide layer over the entire wafer, and then we use the CMP, or again the chemical mechanical polish, because as we grow the thick oxide layer over the entire wafer, it's not going to be flat, and so we'll have bumps where we have the gate formed, and it'll be flatter in the areas where the gates weren't formed, but those bump areas where all the gates are, they would cause problems as we do future patterning steps if we don't try and planarize it again. So we grow the thick oxide, and then we planarize and polish the wafer using the CMP, and now we have a wafer that has our gates and source and drain formed with a thick oxide that is planarized over top of that now. So now that we have our transistors formed all over the wafer, now we just need to actually make contact to the source, drain, gate of our transistors. We'll also, not shown in this particular figure, is we need to make contact to the well areas and the substrate. But again, that's not shown, but it'll be done using the same methods shown here. So let's talk about how we actually make contact and metallize our wafer. So after we have the transistors from the previous step, we will pattern the wafer in order to expose the areas where we want to make contact holes through the thick oxide layer down to the source, drain, and gate. So we'll expose areas, and then using different etch techniques, we'll make contact cuts down to the gate, source, and drain using the contact mask layer, and then we'll etch through the dielectric after we've exposed the areas where we want to etch, and then we will put a metal through the contact holes and a metal pattern for our first layer metal. Now, in older process technologies, they typically used aluminum for the wire material, but in newer process they use copper because copper has a lower resistance than aluminum. Now in the actual hole, the contact hole from the metal layer, metal 1 at the top, the hole where the silicon dioxide is, usually doesn't use the same metal material as the metal layer that you're talking about. And it often uses a plug of tungsten. The reason for using a different metal layer is you want something that will make a good contact resistance to the down to the gate and source and drain, and different metals will have different resistance to the silicide that's down there. And it turns out tungsten has a better contact resistance to the silicide, and also the properties of just filling the hole itself. You want a material that works well for that. And so often tungsten will be used, and then the metal 1 layer will have a contact between tungsten and copper in order to have a good metal 1 resistivity. So basically there's multiple different metal layers that are sometimes used in certain areas. So to sum up, we'll use different metal combinations for different properties in order to get your contact resistance to silicon. You might use one type of metal, adhesion to the silicon and to different base layers depending on what you're doing, the ability to fill the contact hole, the resistivity, long-term reliability. All of these factors will go into what combinations of metals you might want to use. So different fabs might use different combination of metals depending on exactly which materials they're using and what type of resistance they want, etc. So there's a lot of different trade-offs in the metal selection as well. And I'll go into a little bit more on the contacts and metallization in the next foil. So after your transistors are formed, pretty much all of your remaining steps are related to contacts and metallization. And your metallization is the process of building all the wires needed to connect your devices together. Now, building the wires, the metal itself can be deposited in a number of different ways. Three of the main ways are using evaporation or sputtering. There's a couple different evaporation ways that can be done. So evaporation 1, you can basically pass a high current through a wire of a material in a vacuum. So if you wanted to do evaporation of aluminum, for example, you'd have a aluminum wire that you pass a high current through in a vacuum, and you'll have that wire near to your wafer in that vacuum, and as the material vaporizes, as high current is flowing through it, it will vaporize into the vacuum, travel over, and deposit on the wafer. So that's type 1 of evaporation. A different type of doing evaporation, type 2, is instead of passing a high current through a wire, you focus an electron beam at the material, again in a vacuum, and that electron beam hits the material, vaporizes the material, and that vaporized material becomes vapor in the vacuum. Basically vaporizes off of the existing material and travels toward the wafer and deposits on the wafer. Doing it with the E-beam causes a little bit lower contamination on the wafer. You get a higher quality material, but tends to cost a little bit more for that particular equipment. So cost versus quality are two of the things that you can look at. And then the third way of doing metallization is what is called sputtering. So in sputtering, what you do is you generate a gas plasma by, instead of having your wafer in a vacuum, you have your wafer in a chamber with a inert gas, but then you ionize that gas, and then you focus those ions on the material that you want to deposit on the wafer. So you ionize that gas to, like, let's say a positive ions, and then you have your material is put to a negative voltage, so it will attract those ions to the material. The ions hit the material, dislodge the material from where it's sitting, and then the wafer is opposite the material. As the plasma dislodges the material, it travels toward the wafer and then gets deposited on the wafer. So those are three ways that the metal can be used to get deposited on the wafer. And then after you have metal deposited on the wafer across the entire wafer, we can remove it by, first we do a photoresist patterning like we do for all of our other steps, create the pattern we want, and then we can either do a wet or dry etching of the metal. Now a wet etch can be much faster than dry etch typically, and it's basically putting it in a liquid that etches that metal. But because a wet etch is using a liquid to etch, it tends to etch both vertically as well as laterally underneath the photoresist, and so you don't get nearly as dense of metal patterns, and the thicker you make your metal, the wider the width between metal layers has to be. So tend to not use wet etching too often. Dry etching is used much more often, so you create a plasma of a fluorine or chlorine gas, and that gas, in a plasma is ionized, and you can put your wafer at a different voltage, and the gas will basically go toward the wafer, but since it has some momentum in that direction, you'll get much more vertical, sharp etch profiles. Tends to be slower and more expensive, but gets you a much higher density of your metal patterning. So some of the processes that you use for both metallization and removing metal, they might use a certain type of process for your local interconnect and metal 0, metal 1 for your lower level metals, and they might use different process technologies for the higher level metals that aren't quite as dense and have thicker metallization. But what's being used, again, there's always trade-offs for which type of process you're using for which metal layers, and what resistivity you want, what the thickness of the metal is, what the spacing between the metal wires is. So here's an actual photograph, if you will, of a 6-transistor SRAM array. And here you can see a definition of the first few interconnect layers and diffusion, a little bit diffusion. It's kind of hard to really see the diffusion, but the polylines and the metal layers you can see rather plainly here. So, so here, if we look at the bluish lines that are going left to right on the top, that's the metal 1 layer, and then there's round plugs basically between that blue layer and then the layer that's going more vertically. Between the blue layer and the plugs, there's a sort of whitish grayish layer that's going more vertically, and that's what's called local interconnect between the N and P diffusion. So a lot of times when you're doing metallization, you'll have metallization that's mostly one direction. Sometimes it's defined to be exclusively one direction, and then alternating layers tend to go in opposite directions, so 90 degrees off from each other. So you can see that blue layer, then the layer underneath it is going kind of 90 degrees from it, but then they're connected between each other by those round plugs, which are the contacts between layers. And then the polylines are the thin layers. They're kind of going mostly in the same direction as the blue layers, but they're the thin wires that are going kind of left to right for the most part. And then underneath that you can kind of sort of see N diffusion and P diffusion, but it's kind of getting hard to see that. And then there's a box that's being drawn around specifically the 6 transistor SRAM array. You can't really see the transistors very well, but if you take that box and kind of repeat it to the right, you'll see there's 2 cells that look pretty identical and kind of repeating as the 6 transistor array. So this is just kind of interesting to see how things actually look on a real wafer at really small process dimensions. So while transistors and forming your transistors is obviously a very important step in your process technology, the metallization is equally as important. With modern process technologies, here I'm showing a IBM 90 nanometer process technology that was from several years ago. At this stage in process technology, they were doing up to, you can see here, 11 layers worth of metal stack. In current modern process technologies, you might see 13 to 15, depending on how you count your metal layers. So as we are going forward in process technologies, adding more and more metal layers is one additional way of getting additional improvements. Again, every metal layer, it's nice from the standpoint of you have more metal layers that give you better performance, but it adds more cost and potentially lowers your yield because it has additional processing steps. So the thing to note here is at the very, very bottom of the lowest layers, you can see there's the metal 0 at the very bottom is the local interconnect, and then metal 1 through 5 is a certain width and spacing to them, but they tend to have fairly small width and spacing for the lower metal layers, and have around the same width and space as each other. Once you get above metal 5, metal 6 starts getting a little wider, so 6, 7, and 8 will have 2x the minimum width and space as metal 1 through 5, and then the metal 9 and 10 will have 4x that minimum width and space, and so you get wider and wider metals, but fewer and fewer number of lines of metal that you can have, because obviously the wider a metal is allowed to be, and the thicker it is, the less number of lines of metal you have in a given distance. The other thing in this particular process technology, the lower levels of metal were in copper with a low K dielectric. The top layer of metal was in aluminum, and again here you're choosing a different metal layer. Even though it's lower resistance, the aluminum, at least in their estimation, was better for connecting up, since the top layer of metal had to connect up to the pads and the package. Aluminum was deemed better to use as a connection to the package than copper, and so they went with a slightly higher resistance in order to get better connection properties. So again, trading off different parameters depending on the use and connectivity between layers and between package and chip and etc. Are the various different trade-offs you need to think about as you're selecting each individual metal layer. And the thing to note in here, it's kind of hard to tell from this cross-section, but in general, the layers between metal 2 and metal 10 generally only go one direction. So metal 2 might go, across the diagonal that goes from the lower left to the upper right. The even layer metals might go that direction, but the odd layer metals might go from the lower right to the upper left. And generally every other metal layer is perpendicular to the other. So metal 2 might go one direction, metal 3 would go in the direction that's 90 degree shift from that, and then metal 4 goes in the same direction as 2, metal 3 will go in the same direction as 5, and so every other metal layer will go in the perpendicular direction to each other. And then one final figure here, just showing a picture of metallization in a 6-layer copper process by IBM. Not really pointing out anything in particular on this, just showing the intricacies of the metal and the patterning and how the different layers can kind of line up to each other, and it's just kind of interesting to see the intricacy of what can be built with today's modern process technologies.